Hello everybody, we are back in Unit 5 and today we are going to be talking about antiderivatives, also known as integrals. And even though my taskbar is choosing to completely hide it from you, the fundamental theorem of calculus. In case anyone was wondering if I got my tech issues solved. I haven't. Okay, so as you may have guessed by its name, the fundamental theorem of calculus, it's kind of a big deal. There's multiple kind of parts to the fundamental theorem of calculus. And I don't have to say it's a big deal. It's literally named the fundamental theorem of calculus. The AP asks about this constantly. They almost never mention it by name, but the idea of it is everywhere. This is a direct quote on your screen here from, I think not our current textbook, but our older version of the textbook that literally says that this is the most important computational discovery in the history of mathematics, which is kind of a pretty big statement. So I really can't overstate how important the fundamental theorem of calculus is. It's kind of a big one. It's Brian Passwater would call it a non-negotiable. You cannot go into the AP not knowing this. It's right up there with the chain rule. Oh, my taskbar went away. Okay, so the fundamental theorem of calculus has a lot to do with taking integrals. The connection, this connection that they're talking about, this discovery, is the connection between the integral of a function and the derivative of a function. And what they discovered is, or what they, yes, I like to say discovered, the integral of a function undoes the derivative. Now, let's think about that for a minute. Mechanically, if I do the integral, that undoes the derivative, but it's kind of amazing when you really think about what they represent, right? The derivative is the slope of a function, and the integral is the area under the curve. And so I just think it's so fantastic that also it just so happens that even though mechanically, if you take the integral of something, it's going to undo the derivative, but also it's going to get you back to your original function if you took the derivative, which is kind of neat. So what we're really saying here is that derivatives and integrals are inverse operations to one another in simple terms. So like taking this, it's like squaring a number and then taking its square root. And I use that example specifically because when you square a number, you are potentially throwing some information away, right? Like if I square the number -2, I get 4. If I take the square root of 4, there's some doubt as to what my original answer was, right? It might have been 2, it might have been -2. Derivatives and integrals are the same way. When I take a derivative of a function, I am potentially throwing a tiny bit of information away. When you take the derivative of a function, if there's a constant there, that constant goes to 0. So when you try to back that up, when you try to reverse that, we don't really have any way of knowing if there was a constant there and if there was, what it was. We'll talk about that. So if they give us a tiny bit of more information, we can figure out what the constant was. And if not, we cover our butts, and I will show you how we do that. But they are inverse operations of one another. So if you have the function, if you have a function and you take its derivative, you get f prime. If you have f prime and you take its integral, you get f of x back. They undo one another. So we've got to learn how to take derivatives or integrals. We learned how to take derivatives. We learned how to go this way. Now we got to go backwards. All right. So this is my pre-Valentine's Day lesson. When you see an integral sign, I want you to think two things. The first thing that I want you to think is area under the curve, right? Because that's what an integral graphically represents. It represents the area under the curve. Other than that, what you're looking at when you look at an integral is you're looking at somebody's derivative. There was a function, somebody took its derivative, and there it sits. I'm looking at a derivative, and the question is, whose derivative is that? There's an original function somewhere. What was the function? What I'm looking at is a derivative. And so this is why I said to you when we were learning derivatives, I said, you really got to memorize this. You really got to know how to do these, because at some point we're going to be backing this up. undoing everything. So we're about to undo everything we've done, right? I'm going to want to look at a function like, sine of 5x and go, whose derivative is that? And I should be able to figure that out. So here we go. I want you to remember this. This is really important. Everybody is somebody's derivative. Isn't that romantic? It's a really beautiful sentiment. But it's not just in honor of Valentine's Day, it's true. And I say this because we're not going to always be able to find the original function. It's not that the function we're looking at isn't somebody's derivative. It's not that it doesn't have an original function out there somewhere. It's just that we haven't found it yet. Okay, so, and we're not going to be able to find them all. So AP is definitely going to give us some integrals that we cannot do. Not because they can't be done, but because we're not going to learn how to do them. If you go further in your study of math, you will learn how to do them. There are books, volumes and volumes and volumes of books in the library, which probably are very dusty at this point since the advent of the internet, that are called integral tables, where if you have a function, you can go look up what its integral is, because somewhere someone used several sheets of paper and several hours of their life that they're never going to get back and figured out the integral. They figured out whose derivative that was, and then they wrote it down so nobody would ever have to do it again. So there are some that are pretty straightforward to get at. There are some that aren't. We're going to learn a couple techniques for doing it, and then the rest of them we're going to say, okay, that's an integral I don't know how to take. What else is it that they wanted me to do? But please, please, please never forget, if you're looking at an integral, that's the derivative of some function. I may not know what that function is, and I might not even be able to figure it out, but that's somebody's derivative. That's what it represents, that function under the integral sign. Okay, so very quickly, I want to talk to you about the very first rule of derivatives, or God, I keep saying that, integrals. We're going to kind of just unpack all of this in the simplest order we can. So we're going to start this with the power rule. If you remember, the power rule is the very first rule that you learned when you learned to take derivatives. So if we wanted to take the derivative, we multiplied down and then we subtracted 1 from the exponent. So if I were taking the derivative of x cubed, I would do 3x squared. If I were taking the derivative of x cubed plus 6, I would do 3x squared. And notice the plus 6 went to 0. If I were taking the integral of x cubed minus 27, it would still be 3x squared, because again, the constant goes to 0. So what I want you to see here first is what we talked about briefly already. These three functions all have the same derivative. In other words, this plus 6 and this minus 27, all those are vertical shifts. They don't affect the slope of the graph. So what we're going to be doing now is we're going to be starting with 3x squared and going, hey, whose derivative is this? Right? So by writing, what's the integral of 3x squared dx? They're saying, whose derivative is that? I took the derivative of a function. What was the function? The problem is this. It was x cubed and maybe a number being added or subtracted. I don't know. Okay. So we're going to account for that here. So what I want you to note is that we are physically undoing a derivative. Now remember, when we did the derivative, we multiplied by the exponent and then subtracted 1. So again, 3x, take 1 from the exponent, 2. To reverse that, I'm literally going to do opposite operations in the opposite order. So up here, I multiplied and then subtracted. So to undo that, I'm going to add back and then divide. So if I take 3x squared and I add 1 back to the exponent and then divide by that new exponent, look what I get. I get my original back. Okay. The problem is this. All three of these guys had the same derivative. So I don't know which one it was. It might have been x cubed minus 1,000,000. So here's how we cover our butts. We write plus c. And c stands for constant. So what we're saying is this. You said whose derivative is this? Our answer is, oh, There's an entire family of functions whose derivative that is. It's the family of x cubed functions. Okay, so any member of this family, remember in Algebra 2 when you learn families of functions? I love that. So anybody in the cubic family, anybody that's x cubed plus or minus any number, all those are vertical shifts up and down, this is going to be their derivative. So there's not one answer to this. There's an infinite number of answers to this. If you leave this plus c off, that won't be the right answer. And yes, AP will nail you on it. Sorry to tell you. Okay, so we are going to practice with the power rule tomorrow, because just like with derivatives, it's not always as straightforward as, oh, here's an x raised to the power, right? If they give us the integral of x to the fourth, we're going to straight use the power rule on it. We're going to go, okay, add 1 to the exponent, 5, and divide. And then go, plus c, I'm done. But sometimes they get a little sneaky, right? And we're going to look at all the different ways that the power rule comes at us in the form of an integral that sometimes doesn't look that obvious. So we'll practice with that tomorrow. For right now, I think that's enough calculus for the day. Have an excellent evening, and I will see you tomorrow.